Thank you for the invitation to speak, and thank you all for coming. I want to start off by saying that this is joint work with Grodana Matic, Jeremy Van Horn-Morris, and Andy Wan. So I want to start with a little bit of background and motivation, which might bore some of you or not. So let me know if you want more details or just want me to go faster. And I guess, OK, so throughout the talk, I will be focusing on the case of closed tree manifolds. So C is a closed contact tree manifold. But at the end of the talk, if I have some time, I'll also comment on the case of compact manifolds with convex boundary. Okay? So we know, or well, actually, some of you would know that in 3 dimensions, there are 2 types of contact structures. So these are going to be either overtwisted or tight, depending on whether there's a certain type of embedded disk inside the tree manifold or not. So in the case of the existence of such a disk, it's called overtwisted, and otherwise it's called tight. And so what is the relevant feature when it comes to maybe 1 dimension up, or the difference between overtwisted and tight, is that tight contact structures often naturally appear as the boundary of some symplectic form manifold, compact symplectic form manifold. And so we want the symplectic form to be compatible with the contact structure in the sense that the restriction of the symplectic form on the contact plane field is positive. So tight contact structures has that property, and overtwisted ones never do, and that's due to works of Gromov and Eliashberg. But in the case of tight contact structures, there may be also manifolds without that property. So let me say that the ones that are going to be filled by a symplectic form in that sense, or symplectic form manifold in that sense, are called fillable. So therefore, overtwisted ones are non-fillable. And in the case of tight contact structures, we might have non-fillable ones. And so the first examples of these were given by Etnayer Honda and later on by Liska and Stipchis. Or we can be fillable, but fillable in a bunch of different ways. Okay, so the symplectic form that is, or the symplectic manifold that is filling the tight contact manifold could have some extra properties. So the fillable case, we mainly look at three different possibilities. So let me just, maybe it fits here. Let me just say Stein. The Stein fillable ones are the ones coming from, so there are equivalent definitions, various equivalent definitions, but you could think of it as an exact symplectic manifold. So the symplectic form is exact, and there's some gradient-like vector field or Liouville vector field for a certain Morse function whose maximum is attained at the boundary of the manifold. And then there are strongly fillable ones. Let's say strongly. These are the ones that are not globally exact, but exact near the boundary. And some primitive for the symplectic form near the boundary gives you a contact form for the boundary contact manifold. And then there are the ones that are weakly fillable, which are just fillable in the sense we just talked about, that the symplectic form restricts to the contact plane field positively. And just from the definitions, we see that these are, Stein fillable contact structures are strongly fillable, and strongly fillable ones are weakly fillable. But it was shown over time that these inclusions are actually, these are proper inclusions. So these are not, these sets are not equal to each other. So the case of, let's see, the case of this inclusion strongly versus weakly was due to, initially Eliashberg in the case of T3, and then later on by, I think, Ding and Geiges for general T2 bundles over S1. meaning that there are weakly fillable contact structures, but contact manifolds which are not strongly fillable. And then later on, so all of the examples that were given for non-fillable tight contact structures, and then weakly and strongly, and then all of the techniques here involve one way or the other four-dimensional tools. And then later on, this inclusion, whether this inclusion is proper or not, was open for a while until Heegaard Floer came along and Gigini showed that. Maybe I'll just write his name here, because that's relevant to this talk. Using Heegaard Floer homology. Okay? So there are strongly fillable contact structures which are not Stein fillable. He also showed, actually later on, he also showed this inclusion is proper by some additional examples. So therefore, the Heegaard Floer package actually is applicable to showing these kind of inclusions being proper as a whole. So that's why I want to focus on the contact invariants coming from Heegaard Floer homology, and then I will be talking about some refinements of that came up recently. But there's some story behind it, so let me just expand on that a little bit more. OK, so for those of you who don't know what Heegaard Floer package is, so just think of it as some topological invariant. So I guess in its simplest form, let's think of it over the field of two elements, Z mod 2. So this is a graded vector space, HF hat, of some manifold, I guess let's just say M, which further decomposes into direct sum over what are called spin C structures on M. So spin C structures are just oriented two-plane fields up to homotopy outside the tree wall. You could also kind of be rougher about it and just think of them as second cohomology classes. Okay, so this is over basically H upper 2. It's a direct sum over H upper 2, and this is a topological invariant defined by Ozsvath-Szabo. So what happens in the case of a contact tree manifold is that the contact structure being a plane field, and if you're in 3 dimensions, in this case, if we are talking about co-orientable plane fields, which is the case, then it's an oriented two-plane field. So therefore, it actually gives you a canonical spin C structure. So let's say C gives you a canonical SC. And then Ozsvath-Szabo define a distinguished class inside the Heegaard Floer homology for that spin C structure, which is the contact invariant. It's an invariant of the contact structure they show. So therefore, it's a contact invariant from Heegaard Floer homology. So this lives in HF hat of, well, it lives in the Heegaard Floer homology of the tree manifold with the reverse orientation for SC. Okay. So there are some nice properties of this element in the Heegaard Floer homology. So let me just list a few of them that are relevant. So first of all, or some properties. Okay. The first one is that if the contact manifold is overtwisted, then this class is 0. The second one is if the contact manifold has Giroux torsion, which I will just briefly say what it is, then again, the contact invariant is 0. So the Giroux torsion is just an embedded, so it's a T2 cross I with the contact form given by, or contact structure given by the kernel of cosine 2 pi n t dt d theta plus sine 2 pi n t d phi. Okay. So if there is such an embedding, then the manifold is called, embedding in the sense of contact structures, then it's called, the contact manifold is said to have zero torsion, and in that case, we still have the vanishing of the contact invariant. On the other hand, if the manifold is Steinfillable, then the contact invariant is non-zero. And later on, it was observed by Gagini again that you can actually say this for strongly as well, that the contact invariant is non-zero if it is strongly fillable. And just from these properties, it follows that, I guess, what you get is that the vanishing of the contact invariant obstructs fillability. Okay. But you can see that, at least from these properties or these incidences, you can see that the vanishing of the contact invariant relies on the fact that you have some embedded codimension 0 submanifold. In the case of overtwisted, you can think of the neighborhood of an overtwisted disk. And in the case of zero torsion, it's also a codimension 0 submanifold, which makes that vanishing happen. Okay? So based on that observation, that's my assumption at least, that Wendell generalized this geometric obstructions to fillability to an infinite family of such objects. And that's called planar torsion. This is by Chris Wendell. So what are these? These are, it's a little bit, involved, so it's difficult to give the exact definition. But let me just say that a planar K-torsion object is, or a manifold, contact manifold is said to have planar K-torsion if it includes some codimension 0 submanifold, which fibers over the circle with connected and genus 0 fibers with K+1 boundary components. Okay? So then it's called planar K-torsion, or the manifold is said to have planar K-torsion. And so I guess some example that one can think of is that the type of examples that he gives in this paper. You can take, for example, genus 2 surface and cross it to the S1 and think about the S1 invariant contact structure on it, which will make the surface convex. So therefore, you have to have some dividing curves. And you can think of the dividing curves to be these ones. And in this case, you can see that, for example, this annulus cross S1 gives you a planar 1 torsion domain. You've got to be careful. As I said, the definition involves having some extra components of that codimension 0 manifold. So we have to have some non-empty pieces aside from that. So you think of the whole thing as the planar torsion domain. Or you could also have this piece, which has 3 boundary components. Therefore, it gives you planar 2 torsion. So this both has planar 2 torsion domain and planar 1 torsion domain. And if you look at the minimum such K, that will give you the planar torsion. Okay? So that's called PT of MC. As long as you have a finite value. Otherwise, if there's no such thing, then it's infinity. OK. So some properties again. We have, so just quickly, if, well, it's not if actually, it's if and only if. This is more or less from the definition that MKC is overtwisted if and only if PT MKC is 0. And then if MKC has Giroux torsion, then planar torsion it has planar 1 torsion, therefore planar torsion is less than or equal to 1, could still be 0. Let's see, and then if planar torsion is finite, then so non-fillable or not strongly fillable. And then one last thing, I guess. Well, actually, maybe what's really underneath this non-fillability result is if you, OK, so I'm going to link this back to Heegaard Floer, even though he works in a different, he states this result in a different homology theory. I'm going to state it in terms of Heegaard Floer, which is that if the planar torsion is finite, meaning that there's some torsion domain embedded inside like these ones, then the Heegaard Floer contact invariant is 0. So I guess this is actually more directly follows from my work with Steven Sivek and also joint work of Kolangijini and Honda about the isomorphism between Heegaard Floer and ECH homologies. Okay, so these are geometric obstructions which in the end actually tell you that the contact invariant is 0, therefore you have the non-fillability result. So that tells you that you should be able to lift this to some algebraic hierarchy. And that's what Wendel and Lechev does in later work and define algebraic torsion. Question?
Is that weakly fillable?
Which one?
Wendel example?
This?
Is it weakly fillable?
This particular example?
Or are there weakly fillable examples of non?
Yeah, well, you have to look at, you also have to look at if it is weakly fillable or not. You have to look at, there's a twisted version of the, or it's called fully separating planar torsion. And that's an obstruction to being weakly fillable. So there's no obstruction here like that because it's not fully separating. So I'm not quite sure if it is weakly fillable or not, but definitely not strongly fillable. Okay. So the fully separating says that your planar torsion domain, each boundary component, so these dividing curves multiplied with S1 gives you these tori boundary components, and they have to be each separating inside the tree manifold. And in this case, it's not. So you can't say that there's an obstruction. But so I'm not sure if it is weakly fillable or not. OK. So the next one is, as I said, algebraic torsion, which motivates the work we do here. Algebraic torsion. Again, this is Ozsvath-Szabo and Wendel. So they give an algebraic interpretation of the phenomena here. And so, but in terms of the symplectic field theory and in actually every odd dimension, not only in 3 dimensions. So I'm not going to get into the definition, but basically it's, you have some graded algebra and then some differential on it. And the algebra has this formal variable, which is h. And some power of it has to vanish to have algebraic. And so the smallest finite or the smallest power of that variable vanishing gives you the algebraic torsion, AT of MC, as an invariant. And this has the same property or similar properties here. So let me just quickly say that again. MC is overtwisted. Well, similar in the sense that, well, we don't have the if and only statement, but one direction is true. TMC is 0. And then again, MC has 0 torsion. Implies that AT is less than or equal to 1. What else do we have? We have AT MC finite, implies that not strongly fillable. But there's also an additional property here, which you wouldn't see from the planar torsion obstruction. And that's the behavior of this invariant under exact symplectic cobordisms. That also gives you some control over how things change, in particular, for example, when you do Legendrian surgery. And so that says that AT is non-decreasing under exact cobordisms. Okay. Say it again?
This is false for planar torsion, or it's just not known?
Well, I guess it's not known. Or maybe, no, you can't. Well, there's a relationship between algebraic torsion and planar torsion. Planar torsion gives you an upper bound for algebraic torsion, which was something I was just going to say. But you couldn't just use that to deduce that still. So I don't think it's independently known, or I don't think so. Yeah, question?
And this algebraic torsion is computable, or?
So that's the thing. So this is something defined in SFT, and I'm not good at computing things in SFT. I don't know if anybody is. So we figured that we should try to kind of find an analog of this in Heegaard Floer homology, and that was actually something that was made possible by Michael Hutchings. So Hutchings defined an analog of this, an ECH analog of this. ECH is embedded contact homology. It's a homology theory for three manifolds with a contact structure on them. But it happens to be an invariant of the topological invariant of the underlying three manifold. Unless you dig into more of the structure, you can't really get contact invariance just looking at the homology. So defined an ECH analog by filtering the differential in embedded contact homology using the topological complexity of, more or less the topological complexity of the holomorphic curves that he counts. Okay? So what we did is that we took his recipe, basically, okay? And then we applied it to Heegaard Floer. But I should put a remark here to clarify things, especially, because of the fact that this is being recorded. So anybody who sees this lecture by some chance, then they will know that we do not use the Colan-Igini-Honda isomorphism. Between ECH hat and HF hat. Okay. So the idea is to port this recipe to Heegaard Floer by just using what is really going on in the ECH case and just translating it into Heegaard Floer word. And that's possible if you use the cylindrical reformulation of Heegaard Floer homology by Lipschitz. So that's what I'm going to talk about. But that requires, so we use some topological construction of the tree manifold to begin with, and that is the open book decompositions. Just to remind whoever may not remember what open book decompositions are. So let me just quickly say what they are. So open book decompositions. Okay. So these are, well, maybe to be more precise, abstract open book decompositions is a pair of a compact oriented surface with a orientation preserving diffeomorphism. So orientation preserving. And also, it restricts in the neighborhood of the boundary of S. It restricts as the identity. So let's say that S, just for future reference, genus G, and I guess B boundary components. Okay, let's see. And so you can construct a tree-manifold out of the open book decomposition by taking, M, rather SV associated to this is equal to S cross 0, 1. And then you mod out by relations. You just take the cross product with the interval and then glue the two sides. And then you also contract the boundary torus into a circle. That's what you do. So let me just write that. So P, comma 1, identified with phi of P, comma 0, and then also P, comma T is identified with P, comma T prime. Let's say Q. Q in the boundary and TT prime in S1. Okay. So that gives you a tree-manifold. And these things exist by Alexander. So tree-manifolds have these open book decompositions, which is almost a 100-year-old result. But what we are interested in is that the ones that are set to support a given contact structure. Okay? So what that means is that, so S phi supports a given contact tree manifold if M is diffeomorphic to M S phi, and there exists some contact 1 form in M such that, let's see, lambda restricted to the boundary is positive with the boundary orientation on the with the orientation induced by the surface, and then d lambda restricted to S is also positive. Okay, so just a quick diagram to show you what we know about these and the contact structures. So maybe let me just put this on. So we know that, I guess, if you start from open book decompositions or open books, abstract open books, then you can construct contact structures on the resulting tree manifold. So this is Thurston, Winking, Kelper. And then Giroux showed that any two contact structures supported by the same open book decomposition are actually isotopic. So you can actually think of this map into the contact manifolds up to isotopy. And he further showed that for any given contact structure, there's a supporting open book. So this is a surjection. So this is, these two are due to Giroux. It does more, but I'm not going to comment on that yet, because it won't be necessary until we get to some point, and possibly not at all. So, but this is all we need so far. So, okay. So what do we do with an open book decomposition? So now, given the contact tree manifold M, fix some. So pick some open book decomposition supporting MC. Okay, and then what this gives you is a Heegaard decomposition for M, right? So the Heegaard decomposition, so this gives you a Heegaard decomposition. But since we are interested in the manifold with reverse orientation, let's find a Heegaard decomposition for minus M. With Heegaard surface simply given by S cross 1/2, and then union minus S cross, so the S with reverse orientation cross 0. So you just take two copies of the surface at 0 and 1/2, and then you just glue them along their boundary, and that's your Heegaard surface. And the handle bodies for the Heegaard decomposition come from the sweeping the interval from 0 to 1 only halfway for each of the half intervals. So you get the handle bodies of genus determined by the genus of the surface and the boundary components. So that's the Heegaard decomposition. And there's another way to, oh, actually, I could continue here. There's another way to describe the manifold by what is called the Heegaard diagram, which requires choosing a set of arcs on the surface for the case of, well, for the Heegaard surface, I mean, for general Heegaard diagrams, you just have to pick some collection of curves on the Heegaard diagram, which will be indicating where you should glue your two handles to construct your tree manifold. But in the case of open books, you can specify that by picking a collection of arcs. So let's say fix A1 through AN, pairwise disjoint, properly embedded collection of arcs on S, okay. Such that if you cut open the surface along these arcs, the resulting pieces are all homeomorphic to disks. Okay, so such that the complement of, well, okay, union of AIs from 1 to n is the union of disks. So that means that n has to be at least it has to be at least the genus of the Heegaard surface. So that means n is bigger than or equal to 2g minus b plus 1. So if you pick exactly as many as the genus of the Heegaard surface, that's going to be called a basis. But we are just generalizing that and picking something that is that contains a basis, okay, a basis of arcs. Okay, so instead of cutting it into a single disk, it's going to cut into a bunch of disks. Okay, and with this choice, you have the so-called alpha and beta curves. But let me just say actually how we visualize this. Some nice red and blue. This is the convention that Honda Matic uses. So think about this as your surface. So this is S, and these are the boundary components, or they could be the same boundary, it doesn't matter. This is S, so this is your AI. And then you also, so isotope this AI in such a way that you get a copy of it that intersects it in exactly one point, the distinguished point, which we will call xi. for each I. And the corresponding arcs are called BIs. So with AI and BI, we can describe the alpha and beta curves for the Heegaard diagram. So each alpha I is just AI cross 1 over 2 union AI cross 0. So you just, I'm going to probably draw a picture soon, but BI. And then beta I is equal to BI cross 1 over 2, and then union phi of BI cross 0. Okay. So if you just, so this is the picture in the S cross 1/2 page, okay, in the open book decomposition. And then you have the other side of the Heegaard diagram, or the Heegaard surface. And in that, so we're picking for AIs, we're picking the exact same copy. But to get the beta I's, we're going to be picking BI on this portion, and then the action of the monodromy on BI on the other part of the Heegaard diagram. Okay, so that's going to give you a Heegaard diagram for sigma beta alpha, Heegaard diagram for minus m. Okay? Or you could also, alternatively, you could also think of the minus sigma alpha beta. Each describe the same manifold. But to define the Heegaard Floer homology, you also have to choose some base points. Also pick base points, one for each. So one for each component of the complement of these AIs. Yeah, let's just say. But we do that with the following convention. This is Handakaza's Matic convention. So you pick the base point in the component, so in the surface S cross 1/2, in each component of the complement of AI, but outside of these thin strips. Okay. So for example, in the case of n being exactly the genus of the Heegaard surface, you would only put one. But then if you have multiple components, you might have to put multiple. Then, for example, there might be another base point here. Okay, they don't have to coincide. So depends on how the components are positioned. Okay, so you put base points in each component. But then you get a multi-pointed Heegaard diagram. So this gives you a multi-pointed beta alpha z multi-pointed. Heegaard diagram. So now Lipschitz describes the Heegaard Floer chain complex as follows. So formulation or reformulation. Or rather, let's say CF hat sigma beta alpha. So the generators are generated by what are called reap chords, or he calls I chords, which are simply x. So x is a bad notation, but anyway, let's say y. y1 through yn cross I. So where each yi is in some alpha I intersection beta sigma I, where sigma is in the symmetric group with n elements. Okay? So it's in the intersection of alpha and beta curves, but for each I we pick a distinguished point. And so this I will, so later on I will denote this by y. So this is the just an unordered tuple of points, and then this is the I chord. And then you pick a, so what you do is, for the differential, so fix some almost complex structure with the usual properties on, this time, I guess, sigma cross I cross R. And then the differential will count certain holomorphic curves, embedded holomorphic curves in this four manifold. So let's say HF. Say, I'm just going to use X, but OK, let me just use X, and then I will distinguish, which is sum over all Y. And then, so A in pi to hat X, Y, such that index of A is 1 with some and Y. So what this number is, that this is a count of embedded holomorphic curves with boundary on the Lagrangians obtained from these alpha and beta circles by just crossing with R, and which are asymptotic at their punctures to the Reeb chords. They represent a homology class. This is the homology. These are the homology classes of such maps. And then this is the index of that of such a map. So this is a map from a Riemann surface into this almost complex manifold. Okay, and so you count index 1 curves, and then there's a translation, because you pick your almost complex structure translation invariant. So then you mod out by R, that gives you a number, and that's this number here in front of as the coefficient of Y. So this, is a differential, and the homology gives you the Heegaard Floer homology, which happens to be an invariant of the 3 manifold. So we are interested in a particular generator here, and let me just emphasize what that is, and we will denote it by xc. So there's a distinguished element generator xc, which is, so when I write x1 through xn, it's these points, these distinguished points between the AIs and BIs. So the x1 through xn, and then I. Okay? So this I will denote by xc. So this is associated. So this distinguished generator represents the contact class CC inside HF hat. This is a theorem of Matic. So what we want to do is, so with the differential, if you look at the differential, the differential is going to count holomorphic curves coming out of some element. You fix an element, you look at holomorphic curves coming out of it. But if you look at its projection onto the surface, we are looking at things, or domains, so-called domains, which are going to look like, since we are looking at sigma beta alpha, you will have beta curve on your right and then the alpha curve on your left. But that's not going to happen because of the placement of the base points. There's no such thing for this spatial generator. Okay? So that means that the differential of this guy is 0. So therefore, it represents a cycle. That's one thing to prove, to show that it gives you this class. But also that nothing really is coming out of it is essential in what follows when you talk about filtration on this differential. So let me say what we want to do. We want to define a filtration on the differential, which will give us a filtered chain complex out of this. So that's our next step. Okay. So given x and y, so for arbitrary generators, define a function on the yes. So we don't have to specify the index. The moduli space of, well, just to be safe, probably, let's say that the moduli space of curves, embedded curves of dimension less than or equal to 2. Okay, that's enough for our purposes. So that this notation represents that. So we want to define a function on this by picking, let's say, CL. This is a curve, a embedded holomorphic curve satisfying the properties that Lipschitz requires with the boundary and asymptotic conditions. And we want to assign to that curve what is called J plus of CL, which will be simply just the minus the Euler characteristic of CL plus N plus some notation that I will explain in a bit. Okay, so this notation means that, so remember, for each, or let me just say for y and for x as well, this is the number of cycles in sigma. Remember, for each generator of the chain complex, where did I put that? Yeah, here. We have an associated element of the symmetric group, and then the number of cycles, including the trivial cycles, will be this number, and similarly for this guy. So this whole quantity is, so this is an integer. And we want to go one step further and say that actually this quantity doesn't depend on the representative of the homology class, as long as there's an embedded holomorphic representative there. And that follows from a result of Lipschitz. So let me say that Lipschitz says that the Euler characteristic of such a curve is determined by its homology class by the following formula. N minus the index of A plus, let's say, 2 the Euler measure of dA. So the curve, let me just put it here, the curve gives you a homology class in pi 2, or the relative homology classes between x and y. And it also, if you project it, so this is living inside this form manifold, if you project it down to sigma, that's going to give you, a certain chain of regions that the alpha and beta curves cut the Heegaard surface into. And that is denoted by d of A. So that's the domain. And the Euler measure of that domain is this quantity. Okay? So this gives you d of A in sigma. Okay, some integer linear combination of the regions inside the diagram. Okay. So this is Lipschitz's formula for the Euler characteristic. And if you put it together, you see that actually the J plus, as long as the homology class you're looking into is represented by a embedded curve, it doesn't depend on the particular representative you pick. So this means that J plus of CL is equal to index of A minus 2 the Euler measure of dA, and then plus x minus y. Okay. So the right-hand side only depends on A and the endpoints x and y. So therefore, we can actually replace this by just A. Okay. And define it just for every domain. We don't have to just define it for embedded curves. I mean, domains represented by embedded curves. So you can define it that way. But the nice properties that I will say now will follow from assuming that there's a holomorphic representative, embedded holomorphic representative. But OK, so one property that doesn't require that is the additivity, right? So the index is additive under gluing of homology classes, or the sum of the homology classes. And the Euler measure is additive under concatenation of domains. So this tells you that J plus of A1 plus A2 is equal to J plus of A1 plus J plus of A2. So this is one thing we will need to get a filtered chain complex. The second one is if we, so if there's a holomorphic representative, if A is represented by CL, then J plus of A is non-negative, and it's divisible by 2. Okay. So the non-negativity is going to give us a filtration. Okay, so let me just define the filter. Okay. All right, so what we want to do is just decompose this into d0 plus d1 plus dl. Well, so it can go on, but it has to stop because of the compactness. So we make this decomposition, and then we define a filter chain complex CF hat, curly CF hat, which depends on C, phi, and the collection of arcs that we pick, which is going to be simply the sigma beta alpha tensored over F by F the ring of Laurent polynomials. So this is just a formal variable. Okay. So you define this, and then the filtration levels are the obvious ones. So Fp of S phi A are the ones which are going to be written as, let's say, so I less than or equal to P, Ci T to I, and Ci is in CF hat. So these are the filtration levels, and then it's easy to see that we can, just from the additivity, it's easy to see that if I define a differential which is going to be, or if I define a homomorphism as follows, so take Ci T to I, and this is just a finite sum, and then act on it, and that will give me, let's see, this is I. Okay, this is I, and then L, dl Ci, Ti minus L. So this is a differential. On curly CF hat. And this is a filtered chain complex. Okay. So with this, since we have a filtered chain complex, we can try to understand what is the complexity of the collection of curves that could possibly hit the contact generator. The contact generator could vanish, or it may not vanish. But in any case, you might have some chain of holomorphic curves which are eventually hitting it, and then at what level does that happen, or does it ever happen? So depending on that, you get a finite number and an infinity, and that's what we define as our Heegaard Floer analog of algebraic torsion. But what that means formally is that, so the filtered chain complex gives you a spectral sequence let's say EK, S phi, and A, JHF. So these are the pages of the spectral sequence, and then the definition is that okay, AT, S phi, A, and JHF is the minimum k bigger than or equal to 0, such that xc is 0 in ek. Ek plus 1 page, sorry. Okay. If such a finite value exists, then that's the minimum. Otherwise, it's infinity if there's no such thing. Okay. But initially, this quantity depends on all the choices you make, and maybe I'll say just briefly something about that later. So in order to kind of avoid that kind of complication, the cheapest way to get an invariant out of this is that you just look at every possible choice of data like this, and then you minimize over that, because these are all non-negative integers, and if you minimize over that, you certainly get a contact invariant, because you're just piling up all the possible data that is compatible with the given contact structure in one place. So that gives you the contact invariant. So definition is that the AT. So this is bad use of notation, which I regret, but so just keep in mind that this is the Heegaard Floer version, and this is equal to minimum over all AT, S phi, A, and JHF. Okay. All right, so that's an invariant. So this is a contact invariant. So you might say that, well, this is far from being computable, and that's where part of the struggle or part of the war is being battled at this point. But let's say that, let me just say a few, because I don't have too much time, let me just say a few properties of this. So this, okay, so properties, you'll see that this resonates. The properties that I listed for planar torsion and algebraic torsion before. So again, if so MC over twisted implies that algebraic torsion is 0, and this is actually you don't really do too much work here, not at all. I mean, you just have to find a certain to find that this is 0. You just have to find an open book which will realize 0, and that was already provided by Ozsvath-Szabo to show that the contact invariant in this case vanishes. And in that case, the only holomorphic curve that hits the contact generator is a bygone. For bygones, the J plus is 0. So therefore, the contact invariant vanishes in the first page of the spectral sequence. Another property is that, let me do it in the right order maybe. AT MC is non-decreasing under Legendrian surgery. And therefore, I'm not going to write it down, but therefore, it's non-decreasing under Stein-cobordisms, right? So that's similar to the SFT version of algebraic torsion. In that case, they can actually just talk about general exact cobordisms, but in this case, we don't have the necessary topological tools to get to that point yet. But for Stein cobordisms, we do. Okay, the last one, I guess, is that just follows from this, AT. So if MC is time fillable, then, so this implies that AT MC is infinity. And this follows from the fact that, the Legendarian surgery, under Legendarian surgery, this is non-decreasing. All you have to do is just start from the standard contact structure on a connect sum of S1 cross S2s, which is realized by some open book with identity monodromy. And then if you compute just that, that will give you infinity. And then since it's non-decreasing under Legendarian surgery, you get infinity. So it's as simple as that. Okay. So since I'm out of time, let me just say a couple of things about the dependencies here. So the point here is that you can compute this without much effort, just relying on the particular left veering or non-right veering open book decomposition used by Heegaard-Floer. So that gives you 0. But in order to find things that have non-zero algebraic torsion, you really have to find these lower bounds that are non-zero. That's very difficult, and it's actually, in general, very difficult just from the definition to find this data that will compute the actual algebraic torsion, which means that the minimum over all such data. But so what we want to do is you want to get rid of all the dependencies here. So you can do that to some extent. So you can, you would expect that, well, this choice of almost complex structure is redundant. So you take care of that. And then you can also take care of the dependency of phi, within its isotopy class. So you can just think of phi as as some arbitrary member of its isotopy class. So it doesn't depend on the isotopy of phi as well. But those kind of arguments rely on looking at these cobordism maps induced by changes in data. And what you have to do to show that the algebraic torsion doesn't change in those cases is that you define a version of J plus for cobordism holomorphic curves. And that you can do in triple Heegaard diagrams. And once you do that, you just have to check that the induced maps are filtered and the contact generator is sent to the contact generator. So that's what we do. And then therefore, you can get rid of this independence, and then you can reduce this to only the isotopy class of phi. But it turns out that the dependence on the arc collection is kind of essential. You can find an example, an overtwisted example with some bases of arcs for which the algebraic torsion is, for that particular data, the algebraic torsion will be actually non-zero. It will be 1. So that gives you an example where you can't expect it to be arc basis independent or arc collection independent. So what we do to avoid that, we find some restriction on what type of arc collections to look at to achieve independence. And those are complete sets of arcs. So a complete set of arc collection or complete sets of arcs are those which are not only pairwise disjoint, but also they are not isotopic. So you will, for a given surface, you will have 3 times the minus the Euler characteristic many of those. So that kind of cuts the surface into triangles. And for those, it turns out that by applying Pachner moves, these are just the moves which are going to look like, turning this shape into this shape. So think of these as the arcs you have. Then you can show that these kind of moves don't change the algebraic torsion. This you can do. For arc basis changes, it's not possible, but in this case it is. So then what we do is, with that, we can define a new invariant which only depends on the open book, and then we get some control over how things change under positive stabilization and so on. And then that gives us eventually that gives us this statement here, and from that this follows. And some other computability results as well, which I won't get to talk about. So I'll stop here, and if you have any questions, I can answer those maybe in more detail. But thanks.